I got it right for the first time this semester. Maybe I'm turning over a new leaf, huh? All right, so section 5.4 is entitled half angle identities. We have been loading up our toolbox with a whole bunch of identities. I mean, we started off with the simple basic identities, the ratio identities, the reciprocal identities, Pythagorean identities, and then we dealt with the sum and difference identities for sine, cosine, and tangent, and all the other trig functions. And now we're going to deal with, well, we dealt with the double angle identities yesterday for sine, cosine, and the other trig functions. Today, ladies and gentlemen, it's half angle identities. All right, half angle identities. And what does that mean? Well, we'll show you exactly what that entails. Okay, so I'm going to derive the identity for the sine of an angle A divided by 2. That's why they call this a half angle identity, because we're having an angle here. All right, and how to derive this identity? How are we going to do that? Well, we're going to use our double angle identity for cosine to help us out this morning. And there were 3 versions of that identity. Recall, it's always wise to review your math on a daily basis. Recall that one version for the double angle identity for cosine was cosine squared A minus sine squared A. But there were 2 other equivalent versions. Cosine of 2A could be rewritten as 2 cosine squared A minus 1, or there's yet a 3rd version, which says that cosine 2A is 1 minus 2 times the sine squared of A. All right, now, since, ladies and gentlemen, I'm trying to derive an identity for the half angle of the sine function, which of these double angle identities for cosine would I want to use if I just have my sine function present? The first, second, or third one?
Third one.
We're going to use this guy right here to help us derive the half angle identity for the sine. Okay, and I want to point out something very important here. Notice the argument of the cosine function is twice the argument of the sine function, which synonymously implies that the argument of the sine function is half the argument of the cosine function. Isn't that true? All right. So what I'm going to do is I'm going to take this version of our double angle identity for cosine, and I'm going to solve it for the sine function. So here we go. We're going to take cosine 2A, which is 1 minus 2 sine squared A, and we solve for the sine of A. To do that, we subtract 1 from both sides of our equation, or valid identity first. Ones drop out there. And therefore, we got cosine of 2 times an angle A minus 1 is equal to negative 2 sine squared A. Dividing both sides by negative 2 now. All right. And ladies and gentlemen, you see this negative sign on this 2 down here. What I'm going to do is I'm going to put the negative sign out front of the fraction here. Legal to do that. So this negative sign was put out front. Still the same thing. These negative 2's drop out here. I'm left with sine squared A. Now, why did I put that negative sign out there? Well, what I'm going to do is, I'm going to take this negative sign here and I'm going to distribute it into both these terms here. And the effect it has is to toggle the signs here. So after factoring in this or multiplying in this negative sign into both these terms, we will then have, rearranging these terms, we'll have 1 minus cosine 2a over 2. Then, ladies and gentlemen, I'm gonna, in order to solve for the sine of a, take the square root of both sides of this equation. I'm gonna put sine squared a on the left side of this equation too. Harmless thing to do. So let's take the square root of both sides. Now, back in algebra, recall when you were solving, when you're taking the square roots of both sides of an equation, you had to remember to take the, not just the plus square root of the right side, but also the minus square root, so plus or minus. So therefore, the square root of the sine squared of a is just sine of a. And that's going to be equal to the plus or minus square root of 1 minus cosine 2a divided by 2. One last thing to wrap this up, ladies and gentlemen, notice that the relationship between the angle argument of the sine function and the cosine function differ by a factor of 2. So to say the argument of sine function is a and the argument of the cosine function is 2a is to say that the angle of the cosine function here is twice the angle of the sine function. Well, another way of saying that angle A is, or rather 2a is twice the angle A, is to say that angle A is half the angle of the cosine function. So I can replace angle A with a over 2. Hence, the sine of a divided by 2 is equal to plus or minus the square root of 1 minus cosine. Now I replace a with a over 2. The 2's cancel, and this is just angle A now. And there we have it, ladies and gentlemen. We have the half angle identity for the sine function. The half angle identity for the sine function. And why do you think we got this plus or minus notation here? Well, the reason why we got that is because it enables us to assign either the plus or minus sign depending upon what quadrant angle A is in. No, excuse me, what quadrant A over 2 is, what quadrant angle A over 2 is in. So what quadrant A over 2 is in, okay? So depending upon the quadrant that angle A over 2 is in, that will dictate what sign we precede the square root with. That's called the half angle identity for sine. There we go. We have another identity we put in our toolbox. Another identity. Okay. Any questions with the derivation of the half angle identity for the sine function? Utilizing the double angle identity for the cosine function. That enabled us to do this. Why did we use a double angle identity for the cosine function? Because the argument of the cosine function is twice the argument of the sine function, or the argument of the sine function is half the argument of the cosine function. That's why we use that identity. All right, that makes sense. Okay. So, ladies and gentlemen, I got a question for you. Which one of these double angle identities for cosine would we use to derive the half angle identity for cosine? First, second, or third? Well, to derive the half angle identity for the cosine function, we would make use of the second version of the double angle identity for cosine, since it has only the cosine function present. Okay. And we would proceed in a similar fashion. I want everybody to do this one right now. I'll take a piece of paper out if you're able to. And I want you to find the half angle identity for cosine using the double angle identity for cosine right here. Let's find the half angle identity for cosine. All right, so go ahead and try that. I'll give you a minute or so to try to derive that identity. I'll give you a hint. It works the same way as the one I just derived for the sine function, the half angle identity for sine. So this is number 2 in the homework for section 5.4 here. Okay. All right, let's go onward here. One like number 6, the sine of some angle A is -3/5. Angle A is to be greater than 180 degrees and less than 270. They want you to find the sine of A over 2. Well, if angle A is greater than 180 degrees and less than 270 degrees, that places angle A in quadrant 3. So therefore, angle A halves would have to be greater than 90 degrees. Half of 180 degrees is 90, and a half of 270 degrees is 135 degrees. So this would place angle A halves in what quadrant? To be greater than 90 and less than 135 would mean angle A over 2 would be found in quadrant number 2, right? Quadrant 2. All right. So problem number 6 here, they indicate that the sine of angle A is -3/5. They want us to therefore find the sine of A divided by 2. Well, we'll use our identity, our half angle identity for the sine function. And hopefully I can get it correct this time. Because angle A halves is in the second quadrant, the sine of a second quadrant angle is positive. So we'll have a positive sign that precedes the square root. And then we got 1 minus cosine A divided by 2. Do I have that correct according to the identity for the half angle of sine? That looks good, right? So this is the positive square root of 1 minus cosine of A. But ladies and gentlemen, they never indicated what the cosine of angle A is. We just have the sine of angle A. Well, we know angle A is in the third quadrant, so if you want to quickly sketch the third quadrant angle and then build that reference right triangle here. So there's angle A in the third quadrant. We know the sine is -3/5, so sine is y over r, so this must, your y side must be -3, r must be 5. And I'll bet dollars to donuts, using your Pythagorean theorem, you'll find that x must be 4, your 3, 4, 5 right triangle. Because we're in the third quadrant, x must be a -4. True? Okay, now therefore the cosine of angle A is side x over side r. So -4/5 goes in for cosine of A. Now we just have to simplify this. So we have the square root of 1 subtract a -4/5 is 1 + 4/5. Another name for 1 is 5 over 5. So we have 5/5 plus 4/5 divided by 2. So that's the square root of 9/5 divided by 2. 5 comes down and gets multiplied by the 2. So we have the square root of 9/10. Evoking the use of the quotient property for square roots, we can rewrite this as square root of 9 over the square root of 10. The square root of 9 is 3. The square root of 10 cannot be simplified. Rationalizing your denominator, multiplying top and bottom by the square root of 10, ladies and gentlemen, we would have square root of 3 times the square root of 10 over just 10. And this would be your final simplified exact answer for the sine of angle A over 2. 3 square root of 10 over 10. Any questions how we determine that value for number 6? That's one like number 6. If I go too fast, just let me know. I'll slow down. So we have this accounted for, this page here. All right. Move on here. Number 8, ladies and gentlemen, what would be the tangent of A over 2? The tangent of A over 2. Now, the nice thing about number 8 is we're not going to have to reinvent the wheel per se, because the tangent of A over 2 is the ratio of the sine of A over 2 divided by the cosine of A over 2. We already went through this derivation. And since A over 2, again, is in the second quadrant, the tangent of a second quadrant angle is going to be negative. So we'll proceed to square root for the half angle for tangent with a negative. And the identity we derived was 1 minus cosine A divided by 1 plus cosine A. So therefore, the tangent of A over 2 is going to be nothing more than this negative square root of 1 minus. Now, cosine A, we already determined up here, the cosine of angle A was -4/5. So we got 1 minus -4/5 divided by 1 plus -4/5. Simplifying this, 1 subtract the -4/5 is 1 plus 4/5, which is 9/5. 1 plus a -4/5 is 5/5 minus 4/5, which is 1/5. The 5's cancel. We're left with the negative square root of 9, which is simplifies down to just negative what? -3, correct? And that would be your answer. So the tangent of A over 2 would be -3. -3. Any questions how we figured out that one, number 8? We use the half angle identity for tangent. Again, be careful. Make sure you're attaching the correct sign in front of the square root. And you, in order to do that, you're going to have to know in what quadrant your angle A/2 is in. So that's very important. Try not to forget that for a quiz or exam. Most of you are doing a very good job in attaching the correct sign depending upon the quadrant and angles in. Some of you are still missing that. All right, number 8. That was number 8. This is kind of like a repeat thing going on here. Notice in this block of problems, they're actually having us tap into some identities we derived days ago. Like number 20, we would use the sum identity for the what? The cosine function, correct? Cosine A times cosine B minus sine A times sine B. So some of these, and here's a double angle identity for sine and cosecant. So some of these problems are actually reverting back to earlier sections here. So I'm not going to really belabor any of these here. All right, moving on here. Let's try this one. They want you to use half angle formulas to find the exact values for each of the following, meaning that we are not to use our calculator. I was going to entertain one like number 24, the tangent of 15 degrees. The tangent of 15. How would we evaluate the tangent of 15 degrees? Well,
Is it on us to assume that the tangent of 15 degrees means that 15 degrees has already been divided by 2, so it's actually going to be like
well, some other angle was divided by 2 to give us 15 degrees, correct?
yeah.
What would that angle have to be then?
That would be 30 degrees.
Exactly. So, ladies and gentlemen, if we want to tap into our half angle identity here, we have to understand that this angle A/2 is 15 degrees, which implies that angle A is 30 degrees, correct? Now, 15 degrees, notice a little note here that 15 degrees is in the first quadrant. And being the case, the tangent of a first quadrant angle has to be positive. So we will precede the square root of the identity for the half angle of tangent with the plus sign. So we have the plus square root of 1 minus the cosine of 30 degrees divided by 1 plus cosine of 30 degrees using the half angle identity for tangent. Right. I'm using the half angle identity for tangent, which in general looks like this. Notice this angle has to be half these angles. Well, that's the case. 15 degrees is half of these angles. Now we're in business because we understand how to work with our 30-degree angle. We know the exact values for a trig function. So we have the positive square root, 1 minus. Now the cosine of 30 degrees, you could build your 30, 60, 90 triangle or just revert back to the unit circle. At any rate, the cosine of 30 degrees is going to be the square root of 3/2. Cosine of 30 degrees is going to be the square root of 3/2. So how would we simplify this? Please do simplify this. Like if I gave you a question like this on a quiz or exam, I would want you to try to simplify this a little bit here. So what can we do? Well, we know the denominator is 2 here. So 1 could be expressed as 2/2. Likewise. And then what we can do is we can write this as 2 minus the square root of 3/2 divided by 2 plus the square root of 3/2. And these 2's cancel, correct? And therefore we have the square root of 2 minus the square root of 3/2 plus the square root of 3. I would probably accept an answer like this. Although we could maybe go a little bit further. Does anybody know what we could do to further simplify this radicand here? Anything?
Take the square root out of the denominator.
Yeah, exactly. We could eliminate the square root downstairs in this denominator of this fraction here by rationalizing the denominator. In order to do that, we would have to multiply top and bottom of this entire radicand, this quantity underneath the square root, by the conjugate of 2 plus the square root of 3, which is to say that we would multiply top and bottom of this thing by 2 minus square root of 3. Now, when you multiply conjugates together, the product is always going to be the difference between the squares of the terms. Hey, we got a little bonus here. Notice 2 minus the square root of 3 times itself is 2 minus the square root of 3 quantity squared. Downstairs, 2 plus the square root of 3 times 2 minus the square root of 3. The 2 would be squared and give us 4 minus, and we square the square root of 3 to give us 3. But ladies and gentlemen, check this out. We can use the quotient property of square roots. Downstairs, we just have 1, correct? All right. And so therefore this does, what's that?
I'm sorry, why do we use 2 minus square roots of 3 instead of 2 plus square roots of 3?
Let's go back here. Where was I? We want to get rid of this square root down here. We want to rationalize the denominator of this fraction here.
Mm-hmm.
In order to make this square root go away, we would multiply 2 plus the square root of 3 by the conjugate. Its conjugate, which would be 2.
Oh, okay.
You see that there?
Got it. Yes.
And by doing that, because these are conjugates now, the square root's going to disappear downstairs, and it does.
Conjugate. That's what I was looking for. Thank you.
It's gone. Now look at this. This actually works out kind of nice because the numerator is a square root of 2 minus square root of 3 squared, which is just what? 2 minus the square root of 3, and the denominator is 1. So, you know, if you really want to simplify this thing all the way down, your answer would be just 2 minus the square root of 3. That's as simple as it gets. So there's a lot of simplification we poured into this here. So the moral of the story is this: if I give you a problem like this, try to simplify this down a little bit. This is very ugly to leave your answer looking like this. At least, seriously, at least maybe try to take it down to like this, okay? Bare minimum, that would be great. But I'm just showing you that this itself can be further simplified way down. And we showed you how to do that, to take it all the way ultimately down to 2 minus square root of 3 for the final exact answer of the tangent of 15 degrees. All right. That makes sense what just happened there? I know it seems like a lot, but that's what we did there. Took it all the way down. Okay. Yeah, so try to simplify your square roots a little bit. There's a reason for that. Number one, we want you to remain strong with your square roots. Number two, we want you to be able to demonstrate to us that you've learned something out of intermediate algebra when it comes to radicals. It has its place. Okay. All right, that was one like number, what was that? 18? No, 24. Okay. Moving on. Let's see. Okay. One like number 26, the cosine of 75 degrees. They want us to compute the exact value of this. So how are we going to do that? Cosine of 75 degrees. Well, 75 degrees is not one of our nice angles we're accustomed to working with. And so, ladies and gentlemen, we have to try to think to ourselves, how does 75 degrees relate to one of our nice angles, either our 30 or 45 or 60 degree angle? Is there any relationship?
30 plus 45.
Yeah, you know, so one way to do this problem, believe it or not, is just to turn it over to the sum identity for cosine, right? I mean, that will work. Although, you know what, in all honesty, I don't think that was the intention, ladies and gentlemen, on the part of your author, but this would certainly work. And so therefore you would say this is the cosine of 30 degrees times the cosine of 45 degrees minus the sine of 30 degrees times the sine of 45 degrees, utilizing our sum identity for cosine that we've seen 2 days ago. Could we use our half angle identity somehow to evaluate this? 75 degrees, if we want to express it as the half of some angle A, would imply then that angle A would have to be 150 degrees. Isn't that true? So, tell you what, let's try to use our half angle identity formula for cosine. Cosine of A divided by 2 is equal to plus or minus the square root of, do we remember? Can we remember 1 plus cosine of A divided by 2? Do you agree? Half angle identity for cosine. So therefore, the cosine of 75 degrees could be rewritten how? Now, 75 degrees is in what quadrant?
That's in quadrant 1.
Notice that's in quadrant 1. Because of that, the cosine of the first quadrant angle must be positive. So this would be a positive square root of 1 plus the cosine of angle A. Angle A would have to be 150 degrees if this is 75 degrees. And that is divided by 2. Well, you're probably asking yourself or saying to yourself, we've gone from the frying pan to the fire. I mean, 75 degrees was not one of our nice angles. 150 degrees is not one of our nice angles. Or is it? Ladies and gentlemen, 150 degrees is not one of our nice angles, but what is the reference angle to 150 degrees? Anybody?
30.
30 degrees. Notice 150 degree angle puts us in the second quadrant here. And the reference angle for 150 degrees is 30 degrees. And that is one of our nice angles. So we do have a 30, 60, 90 triangle here, correct? So my point is the cosine of 150 degrees is going to be, okay, negative square root of 3 over 2. So this is going to be the positive square root of 1 minus the square root of 3 over 2 divided by 2. You see that there? Which when you simplify this, you'll have the square root of, another name for 1 is 2 over 2. So 2 halves minus the square root of 3 over 2 divided by 2, which is a way of saying the square root of 2 minus the square root of 3 over 2 divided by 2. These 2's would multiply. So we would have the square root of 2 minus the square root of 3 divided by 4, which the square root of 4 is 2. And this remains underneath the square root. So we got the square root of 2 minus the square root of 3 all over what? All over 2. Okay. So that would be your result there. So what we did is we evaluated the cosine of 75 degrees using a half angle identity for cosine. I'm curious, ladies and gentlemen, if we were just to use the sum identity for cosine and evaluate cosine of 75 degrees this way, would the answer to this be the same as this answer? I'm just curious. It has to check out, right? It has to be, consistent. So the cosine of 30 degrees would be what? Cosine of 30 degrees would be the square root of 3 over 2. Cosine of 45 degrees is square root of 2 over 2. Sine of 30 degrees is 1/2. Sine of 45 degrees is square root of 2 over 2. So when we simplify this, we would have the square root of 6 over 4 minus the square root of 2 over 4. My point is, ladies and gentlemen, are these equivalent to each other? Are these equal? They should be. One way to do this problem, cosine of 75 degrees, is use the sum identity for cosine. But another way is we could potentially use the half angle identity for cosine, of which we've done. We got a sloppy answer, messier answer, but are these equivalent to each other? Are these equal to each other? They wouldn't have to be, otherwise there's a contradiction here with our identities. And that would be a very bad thing. If that's the case, then we might find our name in the mathematical journal. Okay, I'm going to evaluate these on my calculator really quickly. I'm going to look at their decimal equivalent forms here to see if this is equal to this. Now, we could make our life easier here and say the square root of 6 minus square root of 2 over 4. I know this is consuming time, but I am curious. So just give me a second here. Divide that by 4. So I'm getting like a decimal, which is about 0.2588. Okay. I'm going to evaluate this now and see if this decimal is equal to this decimal. Let's do this one now. So we got the square root of 2 minus the square root of 3. And then we're going to divide that by 2. Ladies and gentlemen, would you believe I get the same decimal, 0.2588? These are equivalent to each other. Equal. They're equal. They sure don't look like it. They don't look at all like they're equivalent to each other, but they are. So you know what? Whether you do this problem using your sum identity for cosine, or if you do this problem using your half angle identity for cosine, either way, this answer is going to be the same as this answer here. I guess a good challenge problem would be this, ladies and gentlemen. How could you manipulate this to look like this? Or manipulate this to look like this, because they are equal to each other. We've just proven that by computing them in our calculator. You know what I'm saying? That'd be a good challenge problem. They have to be equal. So you should be able to maybe, simplify this down to make it look like this, or vice versa. You get some extra time or have some extra time and want a challenge, try to do that. Try to manipulate this and show that it's this, or manipulate this and show that this is this. Okay. All right, that burned a lot of time, but I wanted to convince ourselves that math is consistent. Okay. All right, that was problem number 26. Onward we go. Ladies and gentlemen, we have the only thing left are proving some of these identities in here, and I don't have much time left, but I don't know. Does anybody see one in here that you would like to see demonstrated? Throw one out on the table, ladies and gentlemen, and I'll try to prove it. Give me one. Go ahead. I'm putting my head on the old chopping block. This is a dangerous thing to say. Give me any problem you choose, and I'll try to do it. One time I got in trouble with that. Some student picked a problem that consumed a half hour. Okay, go ahead, ladies and gentlemen. Pick a problem, 29 to 38. Anybody? Try to stump me. Okay, give me one. They all look so good. I know it's like a kid being in a candy store. We don't know which one to grab first. They all look so tempting. Which one? 29 through 38. Somebody give me one.
35.
30.
That's what I was thinking too, 35.
35. All right. Me and my big mouth. Look at the trouble I've gotten myself into. All right, so I have to try to some way show that the cosine of to the fourth power of theta is equal to 1/4 plus cosine of 2 theta divided by 4. Oops, divided by 2, excuse me. Plus the cosine squared of 2 theta divided by 4. Oh my goodness. What kind of trouble have I gotten myself into? All right, so let's try to prove this as being a valid identity. We're assuming that they are all provable to be valid identities. What side would you think that I should work on, Liz Almond? What side do you think we should work on? Well, the right side does look a little bit more involved, doesn't it, than the left side? Maybe we can go with the right side. You know, I kind of noticed something here with this 1 plus cosine 2 theta plus cosine squared 2 theta. I'm kind of thinking of like maybe a trinomial from algebra. Now I know these denominators are a little different and all that, but I could factor, you know, these denominators out of all three of these terms here. If I factor, for instance, ladies and gentlemen, I'm thinking of maybe factoring a 1/4 out of all three of these terms. And when I do that, I'll have 1 plus 2 cosine 2 theta plus cosine squared 2 theta. Do you buy that? If I factor 1/4 out of this term, and this term, I would leave behind this. Is that true? I think I would. 2 times 1/4 would leave behind this divided by 2, or 1/2 of this, you know? Okay, now, so why did I do that? Why would I want to do something like that? Well, I'm going to rearrange these terms, and now it kind of looks like I have, oops, this, hold on a second. This should be 2 theta plus 2 cosine 2 theta plus 1. You know what, ladies and gentlemen, this kind of mimics, kind of like a trinomial from algebra, kind of mimics like an x squared plus 2x plus 1 structure. Do you agree? Where x is equal to cosine 2 theta. Anybody remember how this factors, this trinomial? This is a special type of trinomial called the perfect square trinomial. Anybody remember factoring perfect square trinomials? This would factor into the square of the square of a binomial.
Which is x plus 1 times x plus 1.
Exactly. X plus 1 times x plus 1, which means x plus 1 quantity what? Squared. That's from algebra. Now, ladies and gentlemen, let's apply it to factoring this inside the parentheses here. Well, it would factor in a similar way. So we would have 1/4 times quantity. Remember, my x is really cosine 2 theta. So replace x with cosine 2 theta. This would factor in a cosine 2 theta plus 1 quantity what? Squared. We all agree. This would become this after factoring this as kind of like a trinomial. You can't call this a trinomial because trinomials involve polynomial constructs. This is a trigonometric construct, but the way we factor this trinomial in algebra, we can employ the same method to factoring this. Okay. All right, so we got this thing down now to 1/4 times the cosine of 2 theta plus 1 quantity squared. Well, that's just great. But how am I'm still a million miles away, it seems, to showing the right side gives me this cosine to the 4th power over here. Seems like I'm still a ways away. Oh boy. So what can we do? Well, we have no choice but to tap into the double angle identity for cosine here that we looked at yesterday. which version of the three would I want to use, knowing that I'm trying to show my right side consists of nothing but a cosine function? What version would I replace this with then? Well, this would get replaced with 2 cosine squared theta minus 1, correct? You agree? Double angle identity for cosine enables me to replace cosine 2 theta with this. Right there. But these ones cancel. And so I'm down to 1/4 times 2 cosine squared theta, quantity squared. But ladies and gentlemen, 2 cosine squared theta squared is going to be 4 cosine to the 4th power of theta. When you square the cosine squared of theta, you get cosine to the 4th power of theta. But these 4's cancel, and I'm done. I have shown that the right side is indeed the what? The right side is indeed, ladies and gentlemen, the left side. You see that there? Okay. So that took us down memory lane, back to algebra, being able to factor a perfect square trinomial, which was good. Good review. Always wise to keep your factoring skills strong.
Good call in 35.
Yeah, nice job. I mean, I was sweating bullets for about 30 seconds after you said do 35. I was thinking to myself, boy, I hope I don't, show myself up in front of the class. I hope I can get this one, and there it is. We got it. All righty. But ladies and gentlemen, I'll be honest with you. I have shown myself up in the past to many classes in the last 27 years. Sometimes you got to be careful in choosing a problem. You got to make sure that you're able to do it, because it's very embarrassing if you cannot demonstrate it in front of like 30 plus students. Pretty embarrassing. It's happened. It's happened though. Okay. I like to think of math as sometimes being this saying: you're always one problem away from having your day being thoroughly ruined in mathematics. You're always one problem away from having your day being thoroughly ruined and making you feel like you know absolutely nothing about math. Okay? It happens. It happens to the best of us. Okay. All right. So that one is in the archives. We have proved that as being a valid identity, number 35. And notice you got other ones here you can practice, and I'll probably assign the odd ones. But hey, if you want extra challenge, you want extra practice, do the even ones too. I'll give you the solutions. I don't know if your author works them out the way you're going to work them out. Normally, author chooses the same side that you would go with, but not always. And if you work it out by choosing the other side and you're not sure about things, you can, get in touch with me and I'll look over your proof and then we'll go from there. Okay. All right. Classwork. Last classwork for the week has arrived. Okay. So I got a couple of problems I would like you to do for August 5th. Class work. So August 5th class work. Problem number 1. I would like you to try one, ladies and gentlemen. I would like you to prove. Oh my gosh. The one I wanted you to do was number 35, the one I just did. I got to choose another one now. Unreal. We can't go with that one. Does anybody else want to pick another one that we can use for our classwork? Anybody? I'm going to have you put your head on the chopping block now. Go ahead, pick one. Other than 35, which one you want for the classwork? Tell you what, let's go with one that looks rather innocent. Number 37, ladies and gentlemen. Let's try to prove that the sine of t halves times the cosine of t halves is equal to 1/2 times the sine of t. Try to argue and prove that one. Number 37, okay? So prove that one. And then problem number 2, I want you to find the exact value of the cosine of 105 degrees. And ladies and gentlemen, I want you to using half angle identity, because you could use the sum identity for cosine again for this one. You could use 45 degrees plus 60 degrees, correct? But I want you to use a half angle identity, because that's the intention of this whole section, is getting used to our half angles. All right, go ahead and do that, and then we'll call it quits. Working with the left side is the longer way to go, ladies and gentlemen, but it, it works. It's more obvious if you work with the left side, but it's the longer way to go. Working with the right side is a quicker way. Let me show you. If you work with the right side, all right, so ladies and gentlemen, I'm going to work with the right side here. Because I see sine, cosine on the left side, I'm thinking, you know what I'm thinking? I'm thinking of tapping into the double angle identity for sine, because I know the sine of 2a is 2 times the sine of a times the cosine of a. Because I see the sine of an angle times the cosine of the same angle, I'm thinking somehow, some way to make the double angle identity for cosine work for me. But how do I make it work for me on the right side? Well, if I go with the right side, what I could do you agree, is I could rewrite this as 1/2 the sine of 2 times t over 2. Ladies and gentlemen, do you buy that these are still equivalent? Are these still equal? Madeline, does it look like these are still equivalent to each other?
I don't think so.
Well, they don't look like it, do they? But you know, what's 2 times t over 2? What happens to these 2's here?
They cancel out.
Cancel out, and it leaves us with the sign of t. So believe it or not, this is still equal to this, ladies and gentlemen. I know it doesn't look like it, but they're still equivalent. Now, why did I do this? Why did I write this way? Well, ladies and gentlemen, here's what I'm going to do now. To help me see the forest for the trees, I'm going to make a little harmless substitution. I'm going to let theta be equal to t over 2. Everybody see that there? Let theta be equal to t over 2. Therefore, my expression can be rewritten as 1/2 times the sine of 2 theta. Everybody see that there? But ladies and gentlemen, we can tap into the double angle identity for sine we learned yesterday now. We can rewrite this. What is the sine of 2 theta? Oh, that's 2 times the sine of theta times the cosine of theta. You see that there? What happens to these 2's though? These 2's cancel out to 1. And we're left with sine theta times cosine theta. But what was theta? What did I let theta be equal to? I let theta be equal to t over 2. So we bring that back now. Replace theta with t over 2. And ladies and gentlemen, I have shown that the right side is the left side. Done. That's one way to show that. That's probably the quickest, slickest way of showing it, but it's far from obvious though. But I wanted to show you this though. This is a common little trick. All right. To make use of a substitution to show this. Did anybody use the left side and argue that the left side is the right side? Curious. Anybody use the left side? I can show the left side, but not right now. If you want to hang on after I get done with number 2, ladies and gentlemen, for me to demonstrate the left side is the right side, I can demonstrate that, okay? But I want to do number 2. Find the exact value of the cosine of 105 degrees. They want you to use a half angle identity. All right. So what do we do? Well, the cosine of 105 degrees, if we call a over 2 equal to 105 degrees, that implies angle A would have to be equal to 210 degrees. So 105 degrees, notice, is in what quadrant? This is in quadrant number 2. So the cosine of a second quadrant angle better be negative. So we'll have a negative square root using the half angle identity for cosine. Negative square root of, what was the identity? 1 plus the cosine of 210 degrees divided by 2. Notice 105 degrees is half 210 degrees. But ladies and gentlemen, 210 degrees is in what quadrant? It's in the 3rd quadrant. What would be the reference angle to 210 degrees?
60.
180 degrees plus how many more degrees gives you 210?
Oh, is it 30?
30 degrees. So we got our 30, 60, 90 triangle. You see that there? And so the sides would be labeled how? If this is a 30-degree reference angle, this would be -1, this would be negative square root of 3, and this would be 2. Do you agree? So now we have the negative square root of 1 plus, but the cosine of 210 degrees is the cosine of the reference angle 30 degrees, which is negative square root of 3 over 2. Negative square root of 3 over 2. And this is over 2. Negative square root. Simplifying this a little bit. 1 is 2 over 2. The 2's multiplied by this 2 down here. So we'll have 2 minus the square root of 3 all over 4. The square root of 4 in the denominator is 2, so we got the square root of 2 minus the square root of 3 over 2. You can leave the answer like that, Liz, that'd be okay. Okay, so that'd be the exact value of the cosine of 105 degrees. Just kind of leave it like that if you want to. That would be all right. Okay. All right, well, if you want to stick around, ladies and gentlemen, I will go back to that identity that I proved by using the right side to show it's the left side. I'm now gonna, if you want to stick around, if you got a couple extra minutes, if you're curious to know how we could argue that the left side is equal to the right side, I'll show you how. All right, so I'll leave it up to you whether you want to stick around or disappear. If you want to disappear, have a great weekend. But I'm gonna redo this proof of this identity and work with the left side and show it's the right side. Okay, so I'm gonna do that now. So how would we argue that? Well, working with the left side, we would have to tap into our half angle identities for the sine and the cosine function. So working with the left side, the sine of t over 2 is going to be replaced with the plus or minus square root of, what was it? What was the identity? What was the identity? We've seen a lot of identities today. What was it? Wait a minute here. It was 1 minus cosine of t divided by 2. That's going to get multiplied by the cosine of t halves, which is plus or minus the square root of 1 plus cosine t divided by 2. True? But like I'm on a positive or a negative times a positive or negative is still going to yield a positive or a negative. Wait a minute. Think about it. Well, hold on a second. Wait a minute here. Positive times a positive is a positive, but a positive times a negative is a negative. So it seems like we would still have the plus or minus notation here. Technically, it seems like it. Anyways, we got a square root times a square root, which means I can multiply my numerators together, which means I got 1 minus cosine t times 1 plus cosine t. And that would sit over 2 times 2, which is 4. Well, what's 1 minus cosine t times 1 plus cosine t? Since these are conjugates of each other, that would give us 1 minus cosine squared t. 4. Well, ladies and gentlemen, what's another name for 1 minus cosine squared t? From a Pythagorean identity, we can replace this with sine squared t. So this is plus or minus the square root of sine squared t over 4. So now when you take the square root of sine squared t over 4, you're going to get sine t over 2. So you get 1/2 sine t. Now, technically, you would have the plus or minus notation out here, but ladies and gentlemen, the plus or minus notation you can do away with because, depending upon what quadrant angle t is in, is going to dictate what sign would go in front of here anyways. Okay, so you can kind of like vanquish that. And so we have shown that the left side essentially is the right side. So that's how you would show the left side is the right side, using your half angle identities for sine and cosine. Okay. So whether you want to work with the left side and show it's the right side, or work with the right side and show it's the left side, it's up to you. All right, have a great weekend. Hopefully I'll see you next week. And we only got 2 more weeks left, so we're almost done.